I'm going to set up an experiment with a magnet. Say that's a magnet, and the north pole is here, the south pole is here, and I'm going to put a loop of, say, a loop of copper wire. Now, I'm going to put a loop of copper wire around here. Just a small loop. Okay, and I have some, I'm going to put some wires, connect some wires to the two ends of the loop, and I want to connect this to something that measures the voltage. I have something to measure the voltage here. Okay. So this magnet would have magnetic field around it, and some of the field would be going through this loop. If I suddenly move this magnet away, we would actually see a voltage that lasts for a short time while I move the magnet away. This is because the magnetic field going through the loop has decreased to zero when I take this magnet away. And it is this change in the magnetic field going through the loop that would cause a voltage, that would actually generate a voltage. Now this effect has a name. This effect, let me write it down, is called it is called electromagnetic induction. Electromagnetic induction. Now what I'd like to do with this little experiment here is to try to understand what are the factors that affect this voltage. See, if I don't move my magnet, there will be no voltage. But if I move the magnet away, then there would be a voltage would appear. But once the magnet is removed, and the magnetic field there has dropped to zero and does not change anymore, the voltage here will stop, will go back to zero. Okay, so let's suppose that I want to do some experiment on here. Now, there would be a magnetic field coming out from the magnet and going through this loop. So let's say, just imagine drawing some field lines going through this loop. So there will be magnetic field lines. Okay, and suppose that the strength of the magnetic field, which I call magnetic flux density, that goes through the loop, suppose that is given by represented by B. Represented by B, and suppose that the area of this loop is A. Now, it's reasonable to expect that the change in the voltage would somehow depend on the strength of the field and maybe also the size of this loop. If I have an extremely small loop, then there might not be so much effect because there isn't much magnetic field going through it. Okay, now and then if you actually set this up and move this back and forth to see how the voltage change, we would also find that if I move this away quickly, I would get a bigger voltage, but it lasts for a shorter time. But if I move it away slowly, I'll get a small voltage, but it might last longer as the field decreases. Now suppose that I also set up some instruments here to measure the strength of the magnetic field, or I would suppose that I just use a piece of magnet that I know, a piece of magnet that I know the strength of. So I would know what is the magnetic flux density near the North Pole. So suppose that I do that. Now, if I imagine writing down some values of what we observe, right? I can imagine making a table of this. Let's say I'm going to say I write down the quantities that I think would affect the voltage. So that would be the time, that would be the magnetic flux density, that would be the area. Okay, and I'm interested in what is the voltage produced. What is the voltage produced for different, perhaps for different times that it takes to move this magnet away, different magnetic flux density, and different area. Right? We want to find out what is the voltage that we see in this time. Okay, and suppose that I'm just going to put in some units for this. Let's say that is in seconds, time is in seconds. Magnetic flux density is in Tesla. Now the area, for now I'm just going to use centimeters squared. Okay, and the voltage is just in volts. Okay, so suppose that for a start, what I do is I'll imagine that I would move this magnet away quite quickly. So it is, at first it is quite close to the loop, and then suddenly I just whip it away. Okay, whip it away so that there would hardly be any magnetic field from this magnet that comes to this loop anymore. So suppose I do it quite quickly, and I actually do it in a very short time of say 0.01 second. That fast. Okay, and suppose that the strength of this magnetic flux density near the North Pole, suppose that it is 0.1 Tesla. Okay, and suppose that I use a loop, a small loop, quite small, of a say area of 1 centimeter squared. 1 centimeter squared. Okay, now I'm going to assume that the North Pole is quite close to the loop, and that the loop is actually it is actually maybe a bit smaller than the North Pole, so that the magnetic field, magnetic flux density is fairly uniform over this area. Right, that means that the lines are still quite straight. They have not spread out very much yet. So that would be that would make things a bit simpler. So suppose I set this up with these values, and then I whip this magnet away in this very short time, and I would quickly take a look at the voltmeter as I whip it away, and I would see a small voltage. Okay, suppose that the voltage that I see is 0.001 volt, and the voltage, I will see this voltage, but it will only be there for a short time, right? Only over the time that I take to move this magnet away. Okay, after that, there's no more change in the magnetic field of magnetic flux density. Then there will be no more voltage. No more voltage will be induced. So for example, suppose that these are the numbers that I actually observed. Now then, the next thing I'm going to do is this. I'm going to change this magnet. Suppose that I change this to another magnet that is twice as strong. Okay, so I get a stronger magnet and put it there. Let's say this new magnet is 0.2, has a 0.2 Tesla of magnetic flux density around its north pole. So I'm going to hold it there, and then I'm going to whip this away in 0.01 second. Again, the loop is the same loop, so the area is still 1 cm squared. But this time, I'll find that when I use this magnet that is 2 times stronger, I'll find that the voltage that I observe down here in the voltmeter, I find that it is also 2 times higher. Okay. So it looks like it might be possible that the induced voltage is actually proportional to the magnetic flux density. Now let me try something else. Let me go back to my first magnet, the one that has a strength of 0.1 Tesla at the North Pole. Okay, but what I'm going to do now is this. I'm going to use a bigger loop. Okay, so I'm going to take out this loop and put a bigger one around here. Let's say the bigger loop has an area of 2 cm squared. Now as I said, I have assumed that the loop is a bit smaller than maybe the thickness of the magnet or the width of the North Pole, so that if I use a slightly bigger loop, slightly bigger area, the field from the North Pole, all of the field from the North Pole will still go through this loop, and it will still be quite uniform. Okay, so I would assume that although the area is bigger, that the field over it is still roughly 0.1 Tesla. So with this new loop, I'm going to repeat my experiment. I'm going to whip this magnet away in this 0.1 second again. I'm going to look at this voltmeter, and I would find, if I actually do that, I would find that the voltage here is also bigger. It would also be roughly doubled. Right, so it would be doubled when the area of this loop is doubled. Right, the important thing here is that the same magnetic field has to cover the whole loop. Okay, so that's why the loop has to be quite small compared to the size of the magnet. If I use a big loop, then obviously the loop will include a lot of area where there is no magnetic field. So those would so we can't really say very much about those. Okay, so assuming that it's still 0.1 Tesla over all of this area, we can then say that from this observation, it looks like if I double the area, I should be comparing with this one. Okay, because it's the first one and the last one that have the same magnetic flux density. So if I double the area from here to here, then the induced voltage would also be doubled. So what this experiment seems to tell us is that the induced voltage is proportional to the magnetic flux density, and that it's also proportional to the area. So what I can do is I can say that I can actually say that the induced voltage is proportional to B times A, to the product. Okay, because if the voltage is proportional to a quantity, say B, and if the voltage is also proportional to another quantity A, then what this means is that the voltage should be proportional to B times A, the product. So this is what we can think of it in this way mathematically, and we can also check this. Let me write out the product of B and A. So let's say I'm going to insert it here, B times A, and B times A. Now B times A down here would be 0.1 times 1, which is 0.1. B times A here is 0.2 times 1, so that's 0.2. B times A here is 0.1 times 2, which is also 0.2. If I compare this with this, you see that from here to here, from 0.1 to 0.2, B times A is doubled. So you see that the number V is also doubled from 0.001 to 0.002. If I go from 0.2 to 0.2, then BA is 0.2 to 0.2, okay, see that the V does not change. But if I so what this suggests is that it agrees with the numbers here, agrees with this relation that voltage, the induced voltage, is proportional to B times A. Okay, and our understanding here is that both the B and the A, both the magnetic flux density and the area of the loop would affect the voltage, the induced voltage. Now, so it becomes useful to think of B times A directly. And in fact, there is a name for this quantity B times A. It is called the flux. It is called the magnetic flux. Magnetic flux. And it's usually denoted by the symbol phi. So it looks like a 0 with a line through it. It's a Greek letter, and it's pronounced phi. In English, one way to write it is PHI. So this quantity, magnetic flux, is defined to be equal to the magnetic flux density times A. Now it's useful to think of this physically. The word flux is kind of related to the word flow. Right? It gives us a sense of something which is flowing, which is moving in some direction. And in fact, that's how we might think of this magnetic field, these magnetic field lines, because we know that the magnetic field lines have directions. They come out of the North Pole. And they go in to the South Pole. So there is a sense of something. We can imagine that it is as if there's something flowing, right? There's a sense of flux. So, for example, like water flowing. Okay. And if you think about it this way, then if we have if you think about these lines as if they have water flowing, then if I have a bigger area, we might imagine that there'll be more water going through the loop. Okay, so that's why it makes sense that B times A, that's one way you can think about B times A. Is a measure, is a way to measure how much of this magnetic field goes through the loop. So now that we know that this quantity, this B times A is a magnetic flux, we might start to understand why B itself was called the magnetic flux density. Let's see. It's, okay. So, right. Let me write this down. Magnetic flux density. So I've mentioned many videos ago that B is called the magnetic flux density, even though it is in a very direct way. B tells us how strong a magnetic field is, but we don't call it magnetic field strength. We call it magnetic flux density, and here is the reason. Here's the reason, because we think of B times A as a magnetic flux. We think of it in this way, that if I have a loop in this magnetic field, then when the loop is bigger, then there's more magnetic flux going through it. Okay, so in this way, then B itself would be equal to, if I rearrange this, I get phi over A. Which is flux over area. So in that sense, B is a kind of density. Is the flux per unit area. Not quite the density as in the density of water, where we think of kilograms per unit volume, mass per unit volume. In this case, it's flux per unit density. But as long as it's per unit something, right? We can, in physics, it's convenient to just call it density, and we'll see this in other situations as well. So magnetic flux density is a density in the sense that it is the flux per unit area, and that actually is the origin of this name, flux density. So let me just finish off by saying that we know that the units of B is Tesla, and the units of A is SI unit would be meter squared. Okay, but this combination of unit, Tesla, meter squared, has a name. It is given the name of Weber. Okay, the short form is WB, and WB is Weber. WEBER. So this then is the units for magnetic flux. This is the unit.